Hi, in this video we're going to do a quick example here. We have a lake that's been stocked with a small number of trout. The population of trout in the lake after time t in months can be approximated by this function. So we're just going to answer a few questions about this function and see if we can understand how it works. So the first thing we want to do is find p of 0. So to find p of 0, I'm just going to plug in 0 for t. So it would look like this. And when I multiply by 0, I'm going to have 250 over 1 plus 9 e to the 0. And e to the power 0 is 1, because any number raised to the 0 power is 1. So I have 250 over 1 plus 9, which is 250 over 10, which is 25. Okay? Now what does that tell us about the number of trout in the lake? This was the initial population of trout. So when the lake was first stocked with trout, they introduced 25 trout into that environment. Okay, so let's look at what happens to this trout population after 1 year's time. So the function time is measured in months. So if we want to find the trout population after 1 year, we should find p of 12, because there are 12 months in a year. So we want to find 250 over 1 plus 9 e to the negative 0.32 times 12. So let's go ahead and do that on our calculator. 250 divided by plus 9 e to the negative 0.32 times 12. Okay, so it looks like 209.478. 209.478. So that means there were around 209 trout in the lake 1 year later. So again, our initial population, we stocked the lake with 25 trout in the beginning. 1 year later, there are now around 209 trout in this lake. Okay, and the last thing we're going to find here is the limit as t approaches infinity of p of t. So we're going to have the limit as t approaches infinity of 250 over 1 plus 9 e to the negative 0.32 t. And if we're going to try to find this limit, I think it's helpful to rewrite the last part of this function using a positive exponent. Instead of 9e raised to this negative exponent, this is going to be equivalent to 9 over e to the positive 0.32t. Okay? Hopefully you recall that any number raised to a negative exponent is just the reciprocal of that number raised to a positive exponent. Okay? So I can rewrite it thusly. Now, in the denominator of this fraction, we've got an exponential function with a positive exponent. So hopefully you remember what an exponential function looks like. It looks like this. Okay, so as t approaches infinity, that means I'm headed this way. Notice the value of this part of the function is just going to grow without bound. Okay, so this number is going to get larger and larger and larger. So this part of the function is going to approach infinity as t approaches infinity. Okay, so if we look at this fraction, 9 over e to the 0.32t, we've got a numerator that is 9. It's a fixed value of 9, and we have a denominator that's getting larger and larger and larger. It's approaching infinity. If we take 9 and divide by very large values, we end up with values that are really close to 0. So this fraction is going to get closer and closer to 0 as t approaches infinity. So what I'm going to be left with here is just 250 over 1 plus 0 as my limit. And that's just going to be 250. Okay. If that's not entirely clear, another thing you can do, you can take a table of values approach to find the limit as t approaches infinity. We've already plugged in a few values of t. Remember, we plugged in 0 and we got 25. We plugged in 12 and we got around 209. So if you wanted to, you could look at a couple more values. You could maybe plug in 20 and 50, and we could just see what's going on as t gets larger and larger and larger. If you plug in 20 on your calculator, you should come up with about 246.317. If you plug in 50, it's 249.9997. And if you go ahead and plug in 100 for t, your calculator actually just gives you 250. It's actually not 250, but it's so close that your calculator sort of gives up and calls it 250. So just looking at these t values, when I plug in larger t values, all that's happening to my trout population is it's getting closer and closer to 250. So that is the limit. So what does that mean? Let's just look at the graph too. Here's a graph of our function that I did on Desmos. So notice a couple things. Here at time 0, it looks like my population is 25. So we started with 25 trout. We looked at the population after 1 year. So 1 year is 12 months. That's going to be right here. So notice the trout population was about 209. Okay, and we said as t approaches infinity, the value of the function, all it's going to do is get closer and closer to 250, which is right in here, halfway between 200 and 300. So we can see that in the graph. Once we get past this year, the trout population grows much more slowly than it did in the beginning. Okay, this is what's called a logistic growth model, and a logistic growth model is good for modeling lots of different populations. So a couple things to notice about this model. In the beginning, when we start with a small population, it looks like exponential growth. Okay, right through here, this looks like an exponential growth model. But somewhere along the lines, we reach this inflection point. And once we get past the inflection point, instead of the population growing faster and faster, that growth starts to slow down. And once we get close to the limit, remember our limit was 250, once we get close to the limit, that population starts to grow very slowly, and in fact it just winds up getting closer and closer to 250 the further we go. 250 is called the carrying capacity. Okay, so theoretically the environment in this lake can only support 250 trout. If we were to wind up with more than 250 trout, essentially that the population would actually fall, and it would get closer and closer to 250. So there's only so much space and so much food to support 250 trout in this lake. So if the population is close to 250, it's not going to grow very fast. But if the population is well below 250, that trout population will go quickly for a while. Thank you for watching.